my screen. Okay, I assume you are reading my slides, so I'm going to start.
Yes.
Okay. So I'm going to present a work that we recently published on a special issue of Intelligent Systems. And it's a work about the definition of a new local homophily measure for node attributed graphs. Node attributed graphs are a particular type of network model where we have information about node properties, node features, node profiling, in addition to the complex relational structure of a graph. And with this, I take the opportunity to introduce this work within the framework, within the context of my PhD project that is about the analysis of feature-rich modeling. So when we deal with complex network tasks, we conceptualize in our mind something like that, because basically we avoid any information about the specific, any domain-specific or context-specific information about a real-world phenomenon in order to abstract and represent, so measure universal principles from a complex systems, such as the well-known scale-free distribution and so on. But within the context of feature-rich modeling, we try to merge and mix universal principles and domain specificity. And why? Because we can define more complex questions, and so we can provide more complex solutions and more complex methodologies of a system. So the focus of today is about homophily. That is the tendency of nodes to connect more likely with similar ones, where this similarity is this kind of similarity, this concept of similarity, depends on the node attributes and node properties. So we study homophily within the modeling of node attributed networks. Homophily is a very important concept in social network analysis. It's an empirical regularity in all social networks, and it was historically defined and modeled by the Newman's associativity coefficient. That is basically a correlation. For instance, here we have a social network where each node is labeled according to the ethnicity, and we can see some kind of segregation here. In network language, this graph is associative with respect to the ethnicity attribute. But one of the limitations of a global score such Newman's associativity coefficient is that it doesn't capture the heterogeneity of connectivity preference within the same network. For instance, in a city, namely in one single graph, we can have segregated regions, but also more uniformly mixed regions. And the global associativity coefficients cannot capture this heterogeneity. For instance, here we have a paradox where each of these 5 graphs have the Newman's coefficient equal to 0. According to this measure, it means that each graph is randomly mixed, but this is true only for the graph labeled as A, while the other ones present an heterogeneity of connectivity preference. So here the idea is to assign to each node an homophilic score in order to study the distribution of the distribution of the associativity with respect to an attribute. And this is not a trivial task, because we can not only consider the the adjacent nodes of a target one due to the universal principles of a network, due for the scale-free distribution of links. Of links probabilities, and it was proposed in the state of the art a variation of the assortativity coefficient, a local variation that deal with the stable state of a random walk. Basically, it performs some type of calculus on the time series created by this random walk, and it is a complex measure, but it works because we can study the distribution of this of the homophily behavior of an attribute. But one of the limitations of this measure, of this variant, of this local variant, is that it doesn't consider the effective distances between nodes. The distance, the concept of distance of path is very important in social network analysis, and it cannot be flattered by a random walk. So we defined this new measure, conformity, that is not a variation of Newman's coefficient, but it's based on a different idea, namely the idea that similar nodes are also close in terms of distances. And basically, for each target node, we calculate a similarity component for each neighborhood at different hops, and then we dump this all these similarity values of each hop according to a decay factor that can be sublinear, linear, or nonlinear. And I prepared also an exercise in order to deal with this measure, but we don't have time to do in detail the exercise, but basically just to see, just to visualize that we have different value components, and with this parameter, with this decay factor, we can dump the importance of different levels. And according to the damping factor that we choose, we can obtain different results, but also coherent with respect to the needs we have. Okay, a real-world example. Okay, that maybe should be more interesting. Okay, these are networks extracted from the so-called Facebook 100 dataset. Namely, they are networks of Facebook friendships for some university college, American university college at the early stage development of Facebook. And each user in this network have information about for instance, the year or of immatriculation. And in this case here, we are studying the conformity, the homophily, with respect to the year attribute. So we can model with this measure complex scenarios because we can see different peaks, and we can clearly see that the peak, the most assortative peak, is composed by first-year students. Basically, this means that first-year students know each other and don't know all the students, or maybe it is some form of segregation of first-year students. Conformity can model more complex scenarios than assortativity coefficient and its variance. For instance, we can deal contextually with the multi-attributes profiling, while the assortativity coefficient is modeled only for one attribute. For instance, if we consider the Smith College, that is an only female American college, if we consider the conformity with respect to gender, we can see how the very few male component of this this network is strongly disassociative. But if we consider the conformity with respect to the pair, gender, and norm, we can see how the female component is the most assertive part of the network. And this is trivial because it just means that we have male dormitories. But it's something that cannot be captured by the other measure defined so far. Also the variance proposed by the multi-scale approach. This is okay. This is a more technical difference between our measure and the multi-scale mixing pattern definition, but it's technical as the exercise, so I can skip it. Okay, and coming back to the context of this work. According to me, the context of feature-rich modeling is very important because feature-rich model is just an umbrella term which generalize already existent model, but we can now combine them, and if we combine more feature-rich models, we can improve our questions, so we can improve our solution and our methodologies. For instance, if we have information not only on node metadata, but also on the time-varying paths, for instance, if we have also a dynamic network, we can improve our questions. We can study, for instance, the impact of homophily in the creation and the evolution of social networks. And now we are our future direction is to define more complex variance alternative of measure. For instance, now we are working on a delta conformity that is basically a conformity dealing with the time-varying paths in order to study homophily and time together. And within the same context, within the same concept and interest in feature-rich models, it's also the same, for instance, if we combine node-attributed networks and multi-layer networks. Here the question can be, what is the impact of different layers in the homophily contribution in a social network? And according to this combination, now we have a collaboration with the University of Exeter, first in studying the assertivity in human mental lexicon, and we are finding some interesting results according to in the field of complex cognitive network science. And okay, that's all for this work. Grazie.
Thank you, Salvatore. I don't know if there are any questions.